Hi folks. So we're picking up from where we left off in class with electronic systems. And you may recall that last time we were talking about building blocks, as I call them, of electronic systems. We talked about passive components, our resistors, capacitors, and inductors. And we started talking about active components, things like our diodes. And so we want to pick up from there. And let's recall that a diode was just a junction of p-doped material and n-doped material. So remember, dopings were silicon with some extra stuff in them. So the p-type has all these extra holes, that's going to give us our positive charge, and the n-type had all these extra electrons, giving us a negative charge. And then we jammed them together at this junction point, and somewhere in the middle it sort of evens out the potential, and that's our depletion region, with an anode and a cathode on either side. And this was our diode. So let's go on from our diode, though, and let's think about what happens when we add on another chunk. So now we've got an N-type on the far left, a P-type in the middle, and this new N plus type on the right. What's the difference between an N and an N plus type? Well, an N-type doping is about 0.1 parts per million, and an N plus type doping is like 100 parts per million. So different concentrations. So looking at this device, we've got 3 terminals here. And what kind of device is this? Did you recall that this is a transistor, and in particular this is an NPN transistor? What we want to do in this session is we want to talk about transistors, and we want to talk about using transistors for signal amplification and for signal switching. So these are some different types of transistors, different packages, different styles. Also, because of the different packages, different heat dissipations, which corresponds to different powers. But they're all doing basically the same thing. They're all either doing amplification or they're doing switching. So amplification is where you're going to apply some sort of low level, low current, low voltage signal, and then the transistor will amplify that using power from something else, like a power supply, to create a high power version of that signal. So that's amplification. We take a low power signal and we amplify it to a high power signal. Alternatively, we can switch, where we use a low power signal to turn on and off that high power signal. But it's not amplification anymore. Now it's just turning it on and or off. One or the other, on or off. So we can amplify or we can switch. There are 2 different constructions of transistors, which leads to different sorts of behaviors. So there's the bipolar junction transistor, or BJT, and there's the field effect transistor, or FET. Here are the NPN and the PNP BJTs. Let's look just at the NPN. So this is the one we were looking at to start with. It's got the N doping, the P doping, and the N plus doping. That's the N, P, and N. You can see in the middle, that's our schematic representation. Let's hope the pen works this time. This is our representation in a circuit diagram. This is also a representation in a circuit diagram. If you put the circle around it, that means it's a discrete component as opposed to being part of a package. But both cases here, we've got the base, that's the P part. We've got the collector, that's the top with the N part. And we've got the emitter, that's the N plus down at the bottom. And so as we apply a current to the base, that's going to allow current to flow from collector to emitter. We apply a current to the base, and that allows current to flow from collector to emitter. Same idea with the PNP, except now we're doing a P with an N with a P plus, so it's a different construction here. And our current at the base, you notice, is going the opposite direction. And the current is now going from emitter to collector. So we've reversed our currents, so you can see that depending on your application, one or the other might be an appropriate choice. But in both cases, we apply a current, and that allows current to flow. Contrast that to a FET, which looks a little different here. We've got an N plus, and a P. Or, here's another FET. These are MOSFETs, by the way. A P plus, and an N. And you can see that the symbols are different, and you can see the construction is different. So the FET is going to have this metal film with an oxide layer. Hey, where do you suppose that MOS part came from? That MO, that's the metal oxide with the oxide layer. And then what will happen is, as we apply our voltage, this time it's voltage, not current, we apply a voltage to that G, that's the gate, and it's going to cause a channel to form between the N plus and the N plus, and that's where we get our N channel. It's a channel of N forming between the N plus and the N plus. And that will allow current to flow in the N channel from drain to source, or in the P channel from source to drain. So again, we're changing the direction of the current through the transistor based on applying a voltage to the gate. We are applying a voltage to allow current to flow. So the BJT, we applied a current to allow current to flow. In the FET, we applied a voltage to allow current to flow. That's the big difference, current controlled versus voltage controlled. So let's go back to the BJT. I said that it's a current controlled, in this case it's a current controlled current source. We are going to describe it using two different quantities here, this alpha and this beta. So alpha is going to give us the ratio of the collector current to the emitter current. So if you look at this, and this is like a Kirchhoff's law sort of thing, we've got base current flowing into the transistor, we've got collector current flowing into the transistor, and we've got emitter current flowing out. So if we look at alpha, alpha is the ratio of how much is going into the collector versus how much is going out of the emitter. So what that's going to tell us is, it's going to give us kind of a guess as to what proportion of the current flow through this is actually what we're wanting versus what proportion of the current is coming from the base, the trigger or the signal that's causing this to happen. Beta is going to give us the collector current, the part that we want, the part that we're controlling, over the base current. So beta is like an amplification factor. How much are we amplifying that base current when we're working in our amplification mode? Beta is amplification, somewhere between 50 and 300, and alpha is more like an efficiency as far as I'm concerned. So we can relate these two because we can say, again, using Kirchhoff's current law, that the emitter current, I sub E, must be the sum of the base current, I sub B, plus the collector current, I sub C. Well, we just defined some terms that are in terms of I sub C, so let's divide left and right sides by I sub C, and we get I sub E divided by I sub C, which, remember, that's 1 over alpha, is equal to 1 plus I sub B over I sub C. Well, that's 1 over beta. So you can rearrange it, and you can put beta in terms of alpha, or you could put alpha in terms of beta, but you can see that these two are connected. This efficiency that as I'm terming in terms of alpha versus this gain in terms of beta, well, they're one and the same. So we can always find an equivalence between these two. And probably what's going to matter most to you is going to be that amplification factor, that's beta, which you're going to see on a spec sheet. So always check your spec sheets. And it might appear as an H or an H sub F or something on the spec sheets. But that's how much current we're getting through the collector by comparison to how much current we put into the base. So we operate in 3 modes, and I apologize, my animations are all screwed up here. We've got the collector current not doing anything. That's our cutoff. That's where things are just hanging out and we haven't done anything whatsoever. We've got the active linear region where we're doing that amplification. We put in some current in the base, we get some current through the collector. And we've got our saturation. And saturation is when we're all the way past amplification, and now the collector current is controlled only by the circuit that it's connected to. So the comparison that I like to make here is to the hose that I've got in the backyard for watering the yard. So when I've got my hose uncoiled and I'm hooking up to the sprinkler or whatever else, I start with that spigot turned all the way off. I have cranked that thing down. There's no water flow. That's cut off. There's no water flow through the hose. Now, as I just start to open the valve and allow water to flow, as I open the valve a little bit more and a little bit more, the water increases, the water flow increases. And so you see that the sprinkler starts spraying further. And it's proportional to how much I've opened that valve. Up until I get to that point where the valve is fully open, and now the limitation is the hose, the limitation is the piping, and so I can keep opening that valve, but it's not going to do anything. So that's my saturation. I have saturated based on the construction of the piping and the hosing. So I start with the valve all the way off. That's my cutoff. I open it just a little bit so I get my active linear where I am opening it a little bit more and the current flow or the water flow is increasing, and eventually I get to saturation where it doesn't matter what I do, I am all the way open and the flow of water is not restricted. Well, it's not restricted by the valve anymore. So that's my 3 modes of the BJT. And we kind of see that in this this plot of the current through the collector, I sub C, plotted against the collector to emitter voltage. And so we've got a region that is cut off where nothing's happening. You can see that in this case, it doesn't matter what the voltage is. There's still very little current flow. There's a little bit, but we can't get it all the way to 0. There's this other region. Let me get a different color here. There's this other region where the voltage doesn't change very much. We're at our saturation voltage, but the current is going very much higher, and that's where we're in saturation. That's where everything is fully open, and we're just allowing the current to flow through, and it's restricted by what's on the circuit. And then there's this other region, the remaining region, and that's our active linear. And that's where the current flow is going to increase, but it's not going to care so much about the voltage across collector to emitter. It's going to care about the base current. So that's where I'm opening the valve just a little bit at a time. And as I open it, which would be increasing the lines here, then the current through is going to increase. And so that's our IC being proportional to IB. This is in the active linear region. So again, the constant of proportionality, the how much do you get out of this, is called the amplification factor. I've listed it as beta, but you may see it as H or HF or HFE in a data sheet. Always check your data sheets. And there's going to be some limit to what can be dissipated by your transistor. Small transistors that don't have a heat sink, well, you can't put too much power through them. And so you can always figure out your power based on your current through the collector and your voltage across V sub, the voltage across C to E, the collector to emitter. So you can work out your power and you can figure out an appropriate amplification factor and choose an appropriate transistor based on your needs. But what about that switching? So that was the amplification, but what about the switching, when we're going back and forth between cutoff and saturation? In cutoff, again, no current flows, so we haven't really applied any current to the base, so IB is 0, IC is close to 0. I mean, there might be some current, but it's functionally close to 0. And the base to emitter voltage is something less than 0.7 volts, and at this point it acts like an open switch. But what happens is I want to close that switch. I'm going to apply enough base current that I'm not going to be in the active linear. I'm going to go straight to the saturation point. And so at that point, the current flow through is controlled only by my circuit, and this is acting as a closed switch. Well, almost a closed switch, because there is going to be a voltage drop across the transistor, just like there's a voltage drop across a diode. But that makes sense because a voltage drop across a diode is based on having that PN junction. And what do you know? I got PN junctions here too. So you'd expect the same sort of behavior. And that voltage drop at saturation is going to be about 0.2 volts. Again, check your spec sheet. So here it is again. If I go from cutoff to saturation, and in this case I've added a little more stuff to it. I've added a resistor at the base so that I can apply a voltage, and then the voltage with my resistor is going to generate my base current. And I've also put in this VCC, which is just some sort of supply. So for instance, that supply could be a plus 5 volts, and a load resistor there, which is going to generate my collector current. And so when the transistor is in cutoff, I've got Vin being small, and so Vin being small means I'm not going to generate that base current to trigger it. And when that is a closed switch then, well, there's nowhere for the current IC to go, so V out must be approximately VCC. This is an open switch, so this means that I can say if Vin is low, V out will be high. Well, if I want to switch this, then I'm going to say, well, Vin is going to be high, the transistor saturates, current flows from VCC down through RL, down through the transistor, and so at that point, V out will be the voltage drop just across the transistor, which would be 0.2 volts, which is pretty close to 0. And so this is a closed switch. Now, it's a closed switch, except that I have to account for that V sub CE, the saturation voltage across the transistor. But again, this is a switch, and it is a current controlled switch. Unless I put that resistor in, then I can make it a voltage controlled switch. And there we go. I can always calculate that the base current using Kirchhoff and using Ohm here, the base current is based on the input voltage, the saturation voltage from B to E, and the resistor that I choose. And my collector current will be based on VCC, the saturation voltage, and RL. So I might need to design RB and RL to protect the device providing V in as well as the transistor itself to avoid excessive power dissipation. So if I'm switching, does it switch instantly? Well, no, not really. It's a physical device. It's not going to be perfect. So if I use exactly that switching case where I'm applying V in and I'm looking V out, I'm going to turn V in on and then off. It's going to be step changes, and we're going to assume that these are perfect steps. And then we're going to compare what happens with the current flow. So what do you suppose it's going to be? Well, just like any real device, it's going to take a little bit of time to get there. If you think back to your dynamic systems, it's kind of like a time-delayed first-order response. So we're going to put in some time scales here. We're going to define the time delay between when Vin turns from off to on and when IC, the current, starts to flow as the delay time, T sub D. And then it's going to take some time for that current to ramp up to its peak value, and we're going to call that the rise time. And you could define the rise time based on going from initial to 90%. Excuse me, that's a yawn because I'm tired. Or you could define the rise time as going from 10% to 90%. It kind of depends on what you're doing. There are different conventions for this. The storage time is the same going down. We're going to have a little bit of a delay between when you turn off Vin and when the current stops moving. So we're going to have a storage time and then a fall time. And if you take those together, delay and rise, storage and fall, then we can call those collectively turn on and turn off times. The turn on time is the delay plus the rise, and the turn off is the storage plus the fall. So there we go. So if I merge these together, that's a terrible line. From the start to the end of the rise, that's the turn on time. From the start to the end of the fall, that's the turn off time. So for the 2N3904 transistor that we happen to have in lab and we'll use a couple of times in class, the delay time is 35 nanoseconds. This is from the spec sheet. Always check the spec sheet. The rise time is 35 nanoseconds. The storage time is 200 nanoseconds, and the fall time is 50 nanoseconds. So you would expect that if you were to measure these, the turn on time would be 70 nanoseconds, and the turn off time would be 250 nanoseconds. It's not uncommon to see it like this, that it's got different times on and off. But what that means is that on a nanosecond level, when you tell it go, it takes a little bit. When you tell it stop, it takes a little bit. When you're dealing on mechanical timescales that are going to be in the tens or hundreds of hertz, this is not a big deal. If you're dealing with RF signals, this might be a big deal, in which case you might want to grab a different transistor. But most of what we're going to do in class is going to be on mechanical timescales. So let's look at an example. Let's look specifically at a BJT as an on-off switch for an LED. And we want to design some resistors. So let's design a resistor RB to protect, it's actually not going to be the transistor. Let's design RB to protect the digital device. Because something is creating V in. It might be your Arduino, it might be something else, but something's creating V in. And so I'm going to assume that it's TTL based, so 5 volts is a high, 0 volts is a low, and that it can supply 40 milliamps. And that's consistent with the Arduinos, that's why I picked these numbers. So I want to design RB such that it works, first of all, and secondly, that it protects that device from trying to supply too much current. So what I'm going to do is I'm going to first draw in that little thing just to connect that. And so now I think you can see that if I go around a loop, I can apply KVL, Kirchhoff's voltage law, and I could say Vn minus Vr, the drop across the resistor, minus VBE at saturation, because I'm assuming that it's a closed switch. If I assume the open switch, well, nothing interesting is happening, so I'm just going to ignore that case for now. And that's all going to sum to 0, because I'm going around the loop, and that's what KVL tells me. So let's move the voltage drop across the resistor to one side and the others to the other side, and let's substitute in Ohm's law for that resistor. So IB RB, that's the current and the resistance. It's going to be Vn minus VBE saturation. And so RB must be Vn minus VBE saturation divided by IB. And again, I gave you the values here. The one value I didn't give you is for this particular transistor. For the transistor, I looked up, I found a spec sheet that gave me 0.6 volts. And I want to say that this was, again, the 2N3904, but I got to double check that. So if we drop in those values, Vn of 5, the VBE saturation of 0.6, the maximum supply of 40 milliamps, what you're going to see is that in order to design for this, the resistor must be at least 110 ohms. And I might go a little further and say, well, if it can supply a maximum of 40 milliamps, I might go even higher and say maybe a kilo ohm. Maybe I'll choose RB to be a kilo ohm. Choose RB to be 1 kilo ohm. And so in that case, I'm going to be looking at about 4 milliamps out, which is probably pretty reasonable. And I'll double check it, but it should work with that transistor. So there we go. Simple KVL and Ohm's law gets me a resistor that will meet my needs. But we still have to do RC. So let's flip ahead and do RC. And in this case, I want to protect the LED and I want to protect that transistor. And so again, I'm going to assume 5-volt supply for VCC just because it happened to be convenient. And I'm going to assume that this is a red LED with a forward bias voltage of 2 volts and a maximum power dissipation of 80 milliwatts. Why these? Because I looked up the particular spec sheet for the LED that I had in lab, and it was a red LED, so the 2-volt forward bias, and an 80 milliwatt power dissipation. So let's do the same sort of thing. Take this over to here just to remind ourselves that we can draw a loop. So here's my loop there, and let's apply KVL. And so I'll get VCC minus VR minus VLED minus VCE, and again I'm assuming that it's turned on, so I'm going to assume saturation is equal to 0. So I'm going to go ahead and solve then for the voltage across the resistor, V sub R. So it's going to be 5 volts minus 2.0 volts minus, and again I didn't tell you that I looked it up, but VCE saturation is going to be 0.3 volts. So minus 0.3 volts. And so the voltage drop across the resistor is going to be 2.7 volts. This one's a little different, though, because that's not enough to design it, but that just tells me what the voltage I expect across that resistor. So now, the second step in this case, to get the current working here, and to get my resistor, is I need to choose the power dissipation. So the power across the LED, or power dissipation by the LED, is going to be the voltage times the current. And so I know that the power dissipation should be less than 80 milliwatts. So the current, now that I know my voltage, the current should be 80 milliwatts divided by 2.7 volts or less, which means it's going to be less than 40 milliamps. Does that have anything to do with the 40 milliamps from the previous slide? No, it doesn't. It just worked out that way when I did the math. Sorry, that wasn't 2.7 volts. What am I thinking? That was 2.0 volts because it was the forward bias voltage. Sorry. So there's my 40 milliamps. And now I can go to my resistor. And the resistance, again, Ohm's law here, should be V over I, which would be, this is where I use my 2.7 volts, divided by my 40 milliamps. And so it should be greater than 67.5 ohms. And again, this is the absolute minimum to keep the power dissipation at 80 milliwatts. I probably want to go less than that so that I get a bright light without cooking it. So I might take it up to 200 ohms just to pick something relatively safe. So I'm going to say choose RC to be 200 ohms. Is 200 ohms a good number? Probably not, because you're not going to necessarily pull a 200 ohm resistor, but you can probably pull a 220, which would be good enough for this. So there we go. We've designed resistors for use in a transistor circuit. We've done some switching, we've done some amplification, so let's look at some other stuff, some other examples of fun transistors. Here's a Darlington pair. A Darlington pair is when I take two BJTs and I'm going to connect the collectors together to the same spot, and the first one's emitter is going to go to the base of the second one. And so what you see here is that as I apply a current to the first one, it's going to allow current to flow through to the base of the second one, and so I'm going to get this double amplification factor. And it's actually not double, it's actually going to be the product. And so the betas on these can exceed 10,000. That's huge amplification. So you might find these in power electronics. We're not going to see them a lot in class, but certainly power electronics is a good application. But notice that the base to emitter voltage, the VBE, is doubled as well. And because you've got this high amplification factor, because you've got a lot of current going here, you're going to need a heatsink. Sorry, you can't read my writing there. That says heatsink. You're going to need a heatsink. Another fun one is a phototransistor. So if you think back to our talk about LEDs and photodiodes, this is the same sort of idea. This transistor, instead of applying a current to the base, is going to apply a light to the base, and that will allow current to flow. So this is slower than a photodiode, but it has this gain, so as I apply more light, I should get more current. So if we put that together with an LED, you get an optical switch. So if, in this case, an optical switch, I've got these two. If the light is shining from the LED onto the phototransistor, well, current is flowing. If the light stops shining, say I have blocked it with a card or something, or I've blocked it with an end stop on a device, well, then the current stops flowing. And so you could use this to locate a position. You could use this to indicate that it's time to start or stop. You could use this to count passes of a rotating device, but each time it passes through there, it's going to interrupt the light, which is going to stop the current flow. Likewise, you could put together this circuit. In this case, we've got an input voltage that's going to go through with the R in there and create a current, which is going to trigger the LED, and now we're going to trigger the transistor, and so V out should turn on and off. This is just like a previous circuit we saw, except now the trigger is based on the light. And so this is an opto-isolator. It's very similar to a diode version that we saw, with a little twist in terms of how you wire it up. It is a little slower though. Still, it's a functional opto-isolator. So where might you see this sort of thing? Well, how about a relay? A relay, as we talked about in class, a mechanical relay is going to rely on a input voltage is going to energize a coil, and that's going to cause a magnetic field that's going to flip a switch. Well, what happens when the physical mechanical switch moves? It could bounce, it could spark. These are bad things. So we could replace that mechanical switch with an LED and a phototransistor or a photodiode. These are different ways to do it. So these are called solid-state relays. So in this bottom left here, you can see that we've got two transistors here. These are phototransistors. These are not BJTs. You can see they're actually FETs. Over here, this is like a photo Darlington pair. Up here, we've got some what appear to be that's either a photodiode or that's a phototransistor. So we've got these different options, right? We can make different types of solid-state relays. So with all that in mind, let's look at the other big class of transistors, and those would be FETs, field effect transistors. So in this case, remember, we're applying a voltage, and we're allowing current to flow. So a voltage-controlled current source. So the first type we might look at is a junction FET. So you can see this is not the MOSFET we looked at before. It's the same idea though. We're going to apply a voltage and current's going to flow. But in this case you can see from the picture that it's symmetric. So the current could go either direction. There's not a choice here. And in this case, we're going to apply that voltage to the gate, and it's going to cause this channel here. You see this channel here in the N region. The channel is going to kind of squeeze shut. And so as we apply this, it's going to squeeze that channel off, and then current's going to stop flowing. So this one's actually a little different. We call it depletion mode. We apply a voltage, the channel shuts off. In a MOSFET, again, here's that construction with that metal oxide and that, the metal gate and the silicon oxide. And in this case, we can have an enhancement mode or a depletion mode. Enhancement meaning that it's going to allow current versus depletion mode, it's going to stop the current. But in this example that's shown here, this is an N channel. Again, as we apply that voltage, the N channel forms between the ends and then current flows. So what makes these different than the BJTs? Well, we're going to have very high input impedance. So we expect that no current is going to flow into the gate, which makes these great for digital. We're also going to see that these are operating on voltage instead of current. That's convenient, which that's based on the high input impedance. They're also relatively cheap to make, which is, I think, why they're taking over everything. And in fact, some things that used to be done by BJTs are now done by MOSFETs. MOSFETs are pretty much everywhere you look. So here's the enhancement mode operation. There's a threshold voltage. That's, the threshold before things happen. And so if you put in the threshold voltage between the gate and the substrate, the N channel forms, and then we get current. And this is going from D, the drain, to S, the source, so down in this picture. But other than that, it's just like the BJT. We apply something and the current flows. In this case, we apply a voltage and then current flows. So just like the BJT, we've got different modes. We've got the cutoff mode where nothing is happening. We've got the saturation. Oh, my animations are screwed up again. We've got the saturation mode, or ohmic mode, where it's acting like a closed switch with that little resistor. And we've got the constant current or active region where we're allowing the current flow to be governed by the voltage that we apply. And in this case, we also have a breakdown region where things go awry, so don't get in the breakdown region. So again, cut off, things are turned off, nothing interesting is happening. The ohmic region, which is our saturation region, which is our switching, so we can switch back and forth between cutoff and saturation. The active region, the constant current region, where we're amplifying, and the transistor breakdown region. So here's our switching back and forth, just like before. If we apply that voltage, Vin, between the gate and the source, then when we have a low voltage below the threshold, nothing interesting happens, we're in cutoff, and now the V out is going to be the same as VDD, it's just a source voltage. When V in is above the threshold, so it's high, the transistor jumps to saturation, and now the switch is closed, except for that little bit of voltage drop across D to S. And so just like before, it's a switch, except in this case, it's a voltage-controlled switch. And in particular, this one, we apply an input voltage that's low, we get an output voltage that's high, we apply an input voltage that's high, we get an output voltage that's low. That's an inverter. So this is the very simplest digital logic device. This is an inverter. And it's one gate and one resistor. So if you think about that, then because we can act as an, I didn't miss one here. There we go. I knew I missed a slide. So if we put two of these together, then we can make what's called complementary metal oxide semiconductor logic. So this is CMOS logic, and this is a CMOS inverter. So now we've got two our FETs in here, MOSFETs, and one of the FETs is hooked up between some supply VDD and the other and the output, and the other is hooked up between the output and ground. And so if I apply a low input, then that lower switch acts like or the lower MOSFET acts like an open switch, and the upper MOSFET acts like a closed switch. And then Vout is connected to VDD. Or if I apply a high input on the right, the lower MOSFET is a closed switch and the upper is an open switch, and so Vout is connected to ground. So this is a different way to do it, using two MOSFETs, and this makes an inverter. So there we go, two different inverter designs using only MOSFETs. So again, BJTs, current-controlled current. MOSFETs are voltage-controlled current. So in the amplification, it's current-controlled or voltage-controlled. And either one of them can act as a switch. And because either one of them can act as a switch, and I just showed you a CMOS inverter, then you can see that either one of them could give rise to logic. And so BJTs are going to give you TTL logic, transistor-transistor logic, which was invented in 1963 by Sylvania, which I think of them for light bulbs, but they also do logic, or at least did. And so what's nice about TTL logic is the power usage does not increase with the clock speed. So it doesn't matter what speed you're going to use the same amount of power. They're also less susceptible than CMOS to static electricity, which not quite as big a deal as it used to be. MOSFET switches give you CMOS logic, which was invented in 1967 by Fairchild. In that case, they don't use any power, or very little power, at idle. So if they're not doing anything, they're not using any power. But conversely, the power is going to scale with the speed. And even though it scales with the speed, it's still going to be very low power overall, which is a great reason to go with CMOS logic, very little power usage. Also, BJTs are going to have your larger current capacity, but slower switching rates and less susceptibility to static. And your MOSFETs have the higher input impedance and normally off. That's why you get your lower power usage. And they're more easily fabricated, and that's going to mean that they're going to be cheaper. They're also less prone to thermal runaway. That's when things heat up and just can't dissipate the heat and then cook. So that's what I've got. That is a short, I think that was about a half an hour, segment on transistors. So the next video in sequence will be, it's Building Blocks Part 2 continued again. So we should talk about some op amps, we should talk about some circuit integration. And then in class, we'll be talking about computer systems.